Okay, so we will start the session for today. This is the tutorial 4 for the course of EE56, which is Nonlinear and Adaptive Control. I'm Anchita Day. I'm working as the PMRF TA for this NPTEL course. I am basically a PhD student and a Prime Minister's Research Fellow at IIT Delhi, working under the supervision of Professor Shubhendu Bhasi. So we will start with the questions that were given in assignment 4 and see how those things can be solved. So we'll mostly focus on giving the hints. Hope the screen is visible. Yeah, it's visible. Okay. So we will start with some of the questions that were mostly based on MRAC and then the robust MRAC techniques. And then we, I think, sir discussed about projection operator, E mod, sigma mod, as well as I think dead zone modification. So yeah, based on this, let us see what the questions are for today's session. So the first question is given by, it's kind of simple. It is simply a norm related question. Let me see. Okay. So it's given that we have two vectors, A that belongs to Rn and B which also belongs to Rn. So it is basically a vector with n elements. Okay, and so this symbol is simply the norm, specifically the 2 norm of a vector. And if we look at the options, see it's kind of a common idea that we have AB on one side and A square plus B square by 2 on the other side. It's something like AB on one side and we have A square by 2 plus B square by 2 on the other side, right? And the common idea that we get by looking into this is that it has something to do with a plus b whole square or a minus b whole square, right? But note that we have two different entities, right? So it's like the symbol here on both sides of the inequalities are positive, which means if you expand this a plus b whole square, you would have something like a square plus 2ab plus b square. And if you do a side change, one symbol would be the opposite. Like, so what I want to mean is that you have a square plus 2ab plus b square. And if you take any of this on the other side, right, just the 2ab or say the a square plus b square part, you end up with something which should be of different sign, right? So you would have a square plus b square on one side and minus 2ab on the other side. On the other hand, if I do expand it for a minus b whole square, I will have a square plus b square on one side and 2ab on the other side. So basically, the a minus b whole square is more relevant to the options that were given to us. Okay, so what we will do is we will play with this a minus b whole square form. And since you can see here we had mod a square or 2 norm of a square by 2 and 2 norm of b square. So instead of taking a minus b whole square, we will focus on 2 norm of a minus 2 norm of b whole square. Okay. So since it is a norm, the first thing, since we are dealing with two norm, it's visible. Yeah. Since we are dealing with two norm, we will have norm of A minus norm of B. Okay. And then the square of it, right? Because you're taking the square of something. We can say, write that this would always be greater than equal to 0, right? For all A and B. So this symbol is for all symbol, okay? So this is true for any value of AB or any vector AB, right? So then if we expand it, so when is it equal to 0? It would be equal to 0 provided norm of A is equal to norm of B. Otherwise, it would always be greater than 0, right? So what we have here is norm of A square minus twice norm of A to norm of B plus norm of B square. This is greater than equal to 0. It's just simple expansion. And then this implies norm of A square plus norm of B square is greater than equal to twice norm of A into norm of B. Now the remaining part is very simple. You just bring 2 on one side, or we can in fact flip this inequality and write it as twice norm of A into norm of B is less than equal to norm of A square plus norm of B square. So then that leaves us with norm of A, I'll just write it there, into norm of B is less than equal to norm of A square by 2 plus norm of B square by 2. And I think this, whatever we have here, is one of the options that were given to us. Okay, so we can just check. I think the option exists. Yeah, so the option is available. So the question was which of this represents, which of this would be correct. So yeah, I think this is obvious. Now you know what the answer is. So next question. I hope there are no doubts. If there are doubts, you can just turn on your mic at any point of time and ask. Okay. So for the next question here is saying that which of the following are correct about the directional derivative of a scalar function f of x along a vector u. So before I go into solving this problem or solving these options, let's just see what we mean by the directional derivative of a function, okay, along a vector u, whatever is given here. So we'll move to the basics. And so if we focus here, so this is already kind of written. I don't have to. So we have heard about derivatives, right? We have done derivatives in our 11th and 12th standards. If you have done diploma and then hearing this course, you would have done it after your diploma course. So derivative is simply saying that, well, if you're given a function, how does it change with respect to the independent variables? And that idea is given to us by this mathematical term called taking derivative or taking differentiation. So when we do differentiation, we have come across ordinary differentiation. We have also studied, I think most of you would have studied partial differentiation as well. So let me just give a quick example. Like if you have f of x equal to x squared, you can see that it's simply a function of x, right? There are no other variables other than x. So df dx, which is the ordinary differentiation, is equal to basically twice x. This is a simple idea of differentiation. Now, instead of this, fx equal to x square, if we had something like f of xy, right? Instead of only one variable, f is now a function of two variables, and this is given by x square plus y square. Then, what would be df dx or what would be df dy? And turns out that since f is a function of two variables, you cannot completely differentiate f with respect to any one of the variables. You need to take something which is called a partial differentiation. That means you would differentiate f with respect to x once and then differentiate f with respect to y. Okay. So what we have instead is differentiate f with respect to x and also differentiate f with respect to y. Okay. And so the symbol, instead of writing this d, we have this other symbol which we call as dou. So instead we use dou f dou x and dou f dou y. And this dou f dou x is basically saying that, well, since it's a partial derivative, we will treat y as a constant. Okay, that means we treat the other independent variables. So, let me just write other variables. We treat the other variables as constants while taking partial derivative of a function with respect to one variable. Okay. So whenever you're differentiating with respect to one variable, you will consider that the remaining all are constants. So if x square plus y square, imagine that y is some constant, say y equal to 4. So you have now x square plus 4. So if this is x square plus 4, the differentiation would lead you to twice x. And then imagine that now x is constant. So if you differentiate this with respect to y, you will get only twice y, right? So this is what is written here. Dou f dou x is equal to 2x and dou f dou y is equal to 2y. So this is the derivative of x with respect to x, okay? And this is the derivative of f with respect to y. And in fact, once we find the derivatives, we actually evaluate them at a given point. So say we have to evaluate this derivative of f with respect to x at the point x naught. And if we do this, it means that we will evaluate this, that is twice x is evaluated when x is equal to x naught. And then the answer would be twice x naught. Say we want to find the derivative of f with respect to x at x equal to 3. So then the answer would be, instead of x, you put 3 and you will have 2 into 3, which is equal to 6. Okay. So the point here is that, see, we found partial derivatives, but we found it with respect to the independent variables that were given to us. Now, what if I want to find the derivative of a function with respect to a different vector? So there is a function in some plane and I want to see how it varies with respect to or in the direction of some other vector instead of this x and y vectors that we took. Okay. So here v would then be a different direction. And if it's a different direction, then what we want to do here is basically that we want to generalize the concept of partial differentiation or the partial derivatives. We are not saying that, well, if the function is dependent on few variables, I will only be finding it, or I will be only finding the partial derivative with respect to those variables. No, we would like to find how the function varies with respect to any given vector of conformable dimensions, of course. So in order to generalize this concept of partial derivatives, we basically use this concept in multivariable calculus. When you have way too many variables, right, and then instead of calling it a derivative or a simple differentiation kind of word, we just use the word directional derivative. Why directional? Because now you want to find the differentiation or the derivative of a function along a certain direction. Okay, so that's why we have this term. Let me just highlight it, which we use as directional derivative. Right, and we do it for a multivariable differentiable function. We can of course do it for a scalar function as well. And we find it along a given vector v at a given point x. So like we last time evaluated it at x naught, in this case we can then find the differentiation or the derivative and then evaluate it at some point x. Okay, x is a generalized point. What does this directional derivative represent intuitively? It tells us that it gives us an idea about the instantaneous rate of change of the function f. Let me just write it down. Of the function f moving through x with a direction specified by v. So it's like you have a function f. Okay, you want to find this derivative along this direction. Okay, now you can find it at different points, right? But you want to focus only on this point, which is x. So that's kind of the concept of doing directional derivative. Now if you're dealing with only scalar function f, then turns out that there are different ways to write a directional derivative. How do you express it with a notation? So you can use this delta symbol. Sorry, it's the nebula symbol. Yeah. So let me just confirm. I don't want to be wrong here. Yeah, that's the nabla. So it's called the it's not called delta, it's the nabla symbol, which simply says that you are taking the derivative of f with along the direction of the vector v and evaluating it at the point x. Okay, we can also write it in this form, fv dash x. So I think most of you have seen this notation, f dash of x. So when we write f dash of x, it means basically we are doing f dash of x along x. That is what it means. Okay. Now if you have you are doing directional derivative, that means you are focusing on a different vector or a different direction. Then you put the notation in the subscript as v here. We can also write it with d f of x with respect in the direction of v, or maybe d f of x and then with respect to v. Or the other is to use this dou sign, dou f of x, and then in the subscript you put v. Okay, so these are also some of the notations. You can give v into nabla fx, or v into dou fx, dou x. Okay, but what like how do you evaluate this? So what is this equal to? This is equal to limit f of x plus hv minus f of x by h where h is tending to 0. That means given a function fx, so given some function f of x value, you increase it incrementally, you increase it a bit. Okay, incremental means with in a very small step. Okay, so incrementally you increase it by h along the direction of v. So if v is your this direction, in this direction you will increase, you will see what's the value of the function f by incrementing the argument, where here the argument is x. So we'll increment the x by a small quantity, which is h times v. So I hope it's clear why we are using v here instead of only using h. In normal cases, we just write f of x plus h minus f of x by h, right? This is what we do usually. But instead of this, we are now focusing on hv as well here. And this v is extra because now we are finding the, it's not coming up, yeah. So now we are finding along the direction of v, where this h tends to 0. That means you would eventually try to bring, so this is your f of x plus hv, this point. So now you want to bring these 2 points really close, okay, and see what is the value. So that's why we do limiting case of h tends to 0, f of x plus hv minus f of x by h. That's how you find the directional derivative for a scalar function f with respect to v evaluated at x. Okay, so if we let me just increase. If we move to the question we had here, which of the following are correct about the, I hope the concept of directional derivative is clear. And since we are dealing with adaptive control where we are using gradient based update laws, so how can we also talk about this directional derivative with respect to gradients? See, gradient is basically telling you how a function is changing. Okay, so let me just write it down first. So yeah, maybe. So what is this gradient of fx? If I say gradient of a function f of x is simply the rate at which f of x is changing with respect to, something, some independent variable. Might be if you're dealing with partial derivatives, the variables will change. If it's right now, we are I've only written it in terms of f of x. So maybe I can just say f to generalize it. Okay. So gradient of this function f is a vector. So if we are looking at it mathematically, that nabla symbol that we had, this symbol, yeah, this symbol is also a way to express gradient. Okay. So gradient of a function is a vector containing the partial derivatives of f with respect to each component of the argument vector, right? So for example, if we have, say, let me see, not example, let me just, yeah, you can give it as an example. Say my x vector is made up of, this is my argument, x1, x2, x3. Okay. Then grad f, so this is a way to write the gradient symbol. So see, you can just a minute, it's not appearing. Yeah. So we have grad f here, and with respect to x, because we are doing a normal differentiation, we are not talking about any directional derivative right now. That means we are taking it in the direction of x, because that's the only vector we have. So then grad f with respect to x is simply dou f dou x1 dou f dou x2 and dou f dou x3. Okay. So how much time do we have? We have time. Let me give you an example. Yeah, I can maybe do this again. So it's the same example we had. F of x is equal to x squared, where x belongs to R. That means x is a scalar quantity. Then grad f x is simply twice x. Now what if f of x is equal to, say, x squared plus y squared? Again, I'll just take the simple one. So I think, yeah, I've done a small mistake. Should be f of x comma y is equal to x squared plus y squared. Okay. So in this case, we simply have that grad f would be dou f dou x and then dou f dou y. So then we can write it as twice x twice y. Okay. What about some other function? Let me say f of x is equal to x1 square x2, where x is made up of x1 x2. What would be my grad f? It would be again the same dou f dou x1 and then dou f dou x2. Right? So first we treat x2 as a constant. So then we will have twice x1 x2. And then we treat x1 as a constant. So we simply have x1 squared. Okay. So this is the simple idea about gradient. Now if we, I think we can look at the directional derivative idea. So when we focus on this question, what do we understand by directional derivative is that so this is same as saying that we want to find the projection of the gradient of f of x. I hope it's visible. F of x in the direction of u, which simply is equal to the rate of change of f of x in the direction of u. So this rate of change is basically what we get from the gradient function. So if we evaluate, our option was given to be this, right? So if you remember the notations that we had, all right, we can simply do this grad yes. So we have this grad ft u, which is equal to, then simply if we follow the definition, this was the notation, right? And if we this is the notation that we had, and if we follow it, we will simply have limit h tends to 0 f of x plus h in the direction of u, so we have hu minus f of x divided by h, and that gives away your answer. Okay, I hope this option is there. Yeah, it's there. Okay. So we will now move on to the next question. it's kind of easy. Which of the following functions are convex? So what do we mean by convex functions? That's kind of the first thing to talk about, right? So any idea, like if you have, I think you have idea because sir might have talked about it in the class. So convex function, say a function is given to you f of x. Okay, we will say that the function is convex if, suppose, let me just show it graphically first. Say this is a function given to you. Okay, now by the name, also by whatever we I think we read about convex and concave lens in our 11th or 12th standards. So if we correlate with that idea, we kind of see that whatever looks like a bowl or something that can contain water, if you pour on it from the top, then that is a convex function. That's the very simple way to look into this convexity property. So what it simply says is that, well, uh, take 2 points. I choose these 2 points, right? And I join the line segment. So if this line segment lies above the function, then it is a convex function. Okay. If it lies below the this function that was given to us, then it would have been concave, but now it lies above it, right? So if you have to write it in a mathematical way, you can say that, well, let this point be x1, let this point be x2, and what you are basically finding here is that you are saying, well, each of these points that's been given to us here, so this was your x1, right? And this was your x2. Now if you focus here, if I like kind of, I don't know how to make it, if I zoom it for you, you can see that any point, this is my x1, this is my x2, any point on this line segment, this segment can be expressed as, say, some point P, which is equal to lambda into x1 plus 1 minus lambda into x2, where lambda is between 0 to 1. Okay. Right. So basically this is the green segment that we had. Right. And what about this portion, this blue line segment that you see? So this is nothing but your f of x2, and this point is your f of x1. Okay, it's taking time. Yeah. So whatever section you have, if I zoom this part, whatever section you have here, any point here can be written as lambda of f of x1 plus 1 minus lambda f of x2, where lambda belongs to 0 to 1. Okay. So turns out that since this blue line segment is lying above the this pink line or the function that was given to us, what we have here is that for convexity, we just have f of lambda x1 plus 1 minus lambda x2 should be always less than equal to lambda f of x1 plus 1 minus lambda f of x2, right? If this condition is satisfied by any given function for any 2 points x1, x2 at any lambda between 0 to 1, then we say that the function is convex. If it's the opposite sign, if it is greater than equal to, then we say it is concave. Okay. Interestingly, if it is simply less than or simply greater than, then we call it to be strictly convex or strictly concave. Why strictly? Because it will never touch the points. Okay. So now there are there are several other ways to test convexity. So I will just give a small figure to you. See, in this case, if I draw this very function, then this is also a convex function. You can take any 2 points and it would always be lying above or on the line segment, but never below. Okay, did I write this? Yeah, it will never lie. You take any 2 points here and here, join them, and then this joint line segment will never lie below the red line. So this function is also convex, right? What about this one? So if I do this, you can see that at this small portion that we have, there it's simply a straight, kind of a straight line segment, and then it's going up. So if you join any 2 points here, it would lie exactly above the function. But if you take 2 points here, then it is lying equal to on, like that means on the same part as the function itself, but never below. So this is also convex. But turns out that neither of them are strictly convex. Why? Because for strict convexity, what we need is that it will never lie on the line segment. It would only be above the function. Okay. So say we have this function. Now wherever you join, whichever point you connect here, it will, the line segment is always above the given function. So that means this is now strictly convex. An example is simply y equal to x square. Okay, this is a strictly convex function. Similarly, you can draw the opposite of it. Say you have a function like this. Now this is your strictly concave function. Okay, so that's the idea about strictly convex and strictly concave. So I'll just remove it because I already talked about it. Now let's look at some of the methods to test convexity, because that was the question. Like we had to find which of the given functions were convex. So there are several methods, but we will focus on only some of them. For example, we have one is the first derivative must be non-decreasing in nature, and the second derivative must be non-negative. If this is true, then a function is convex. For convexity, now of course it can be used for only functions that are twice differentiable, because you're doing differentiation twice, right? So what about the second method? We have another method involving the Hessian of a matrix, right? Like Jacobian, we also have, what is Jacobian? Jacobian is if you're finding the derivative only, that means you're doing derivative only once. Okay, then you get the Jacobian. And if you do the derivative twice, then you land up with something called the Hessian matrix. So for the Hessian matrix, which I will show what it looks like, must be positive semi-definite. So just as a side, okay, a side, we can also say if the Hessian, I'll just write it as H here, right? If the Hessian is positive definite, then we have a strictly convex function. If the Hessian is negative semi-definite, then we have a concave function. And if the Hessian is negative definite, then it's quite obvious we will have a strictly concave function. Okay. So the Hessian matrix has to be, how do we find a Hessian? Just to give you I can give you a quick example. Say you have a function f, which is a function of three variables, x, y, and z. Okay. So here the Hessian, I will write it with simply h, is equal to because we are doing twice differentiation here, dou to x dou f square. Let me just write it down. That means you will take all possible combinations of differentiating with then with y, and then x with x, x with z, so on and so forth with like y, 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 z, y, x. Okay. So we have dou to f, dou x, dou z. So this right here is your Hessian matrix. Now, if you evaluate it and if you can show that this is positive semi-definite, then that means your given thing is a convex function. You write it down. Then it is a convex function. So if we just move forth, because we have some other question regarding convex set. So let me cover it up right now. What is a convex set? A convex set is simply a set that would satisfy kind of the same property as we discussed for a function. So given this set which doesn't look that convex, so yeah, yeah, I think this is better. So pardon my drawing is not that exact, but so what do we mean by a convex set? Now you take any 2 point on this set, including the boundary if you want, if the boundary is included, then you join it, and then the joined line segment should lie inside the set. That's the simple idea. Okay. So it doesn't have to be in the interior of the set, but it should belong to the set as well. So the joined line segment should also belong to the set. Then we say for any 2 points in the set. Any 2 points in the set. The joined line segment should also belong to that set. So basically, if you have to write it mathematically, you will just say that if x1 belongs to some set, say S, I call it S, okay, and x2 belongs to S, then S is convex if and only if, or let me just say S is said to be convex if, that makes more sense. S is said to be convex if lambda x1 plus 1 minus lambda x2 also belongs to S for all lambda in 0 to 1. Okay. And then if we kind of, proceed with the same idea of convex and concave functions, then what are affine functions? Basically, if something is affine, it means it's like a straight line. It's linear, simply put. Okay. So affine functions are functions that are both convex and concave. Okay. And it satisfies the linearity property. Therefore, if something is, if you recall, we had this notion, right? F of lambda x1 plus 1 minus lambda x2 was something related to f of x1 plus 1 minus lambda something related to f of x2. Now for convexity, we had this thing as greater than, sorry, less than equal to. We had less than equal to, right? For a concave function, we had it to be greater than equal to, right? But if something is both concave and convex, that means the only symbol that can be placed here is the equal to sign, right? That means this would be equal to lambda f of x1 plus 1 minus lambda f of x2. If this is satisfied for, of course, now you don't have to worry about lambda being particularly in 0 to 1, it can be any real value. And then we say that the function would be affine. Okay. So yeah, that was too much basics being discussed, but let's just move back to solving the business. So now we know what are convex functions, right? If you have to think it in a pictorial format, just think it like some function if on which if you pour water, it would be collected. Okay, it won't fall off. So an easy way, like you have to find out which of the following functions are convex, and the easy way to do this, just a minute. Yeah, the easy way is to go with plotting the functions with x as the independent variable. So what if we plot them? Let's just see if it matches with our analytical derivations that we'll do later. So plot of e to the power ax, that's the function given to us. E to the power ax, what I've done is I've plotted it here using Desmos for different values of a, right? We do not have any limit on a given here. So I take a to be equal to 0 and I get this line, which is a line simply. With a equal to minus 2, it is this function shown in red. I hope it's visible to all of you. Yeah. With this green one, this is for a equal to 2. A equal to 100 is with this black dashed line. And the dotted one is for a equal to minus 100. Okay. Now turns out that in any of the cases you can see is something where if you join any 2 points, the line segment would always be on or above the given function, right? So in each of these cases, we see that the functions are convex. Particularly for a equal to 0, we have it to be affine, right? But for all the other cases, it is convex, and an affine is both convex and concave. So the conclusion that we have from here is that this is a convex function. So we have this to be convex. What about the next function? We have log x to the base e, right? And if we plot it, we just get this very function. Now you can see any 2 point you join, it would always lie below the given curve, right? You can join 2 points here. It should lie on or below the curve, right? So this lies below the curve. If you join 2 points here, it's lying on the curve. Is that it? So it's on or below curve, and therefore this is a concave function. So what we can conclude is this is concave in nature. The third option given to us was plot of mod x to the power a with a being greater than equal to 1. So again, we can just plot. If a is equal to 1, then of course it's the simple modulus function that we have. If a is equal to say 5, I've taken, this is the blue curve that I get. With a equal to 100, I get this green curve. In all of the cases, we just see that the function is convex, right? It's very clearly visible. So we have it to be convex. And then the last one, plot of x into logarithm of x to the base e. And turns out that you can see this is also a convex function, right? It's very clear. You can join 2 points here, it would lie above the curve. You can join 2 points here and here, it would again lie above the curve. So this is also a convex function. Now that's the easy thing to do, but in all scenarios you won't be able to plot the functions. So how do you proceed then? That's where we deal with those methods to test convexity. So we will now do it without plotting. You can refer to the basics that were written earlier. So I think I can discuss the third method as well. Okay, yeah, so I just left out one method. I won't say it's a method, it's simply the same testing condition that we have, which is the basic definition. I'll just add a point here. So the third condition is simply check that f of x Okay, so we'll just check the simple condition or the definition of convexity is basically that you test the definition itself. Okay, so if we go back now and start analyzing them without plotting right now, let's just see what are the answers. So the first function I think was given to be e to the power ax. Right? So f dash x, if you recall, is same as writing the nabla symbol. So is equal to a e to the power ax. A square e to the power ax, right? So let's first focus on the first derivative. The first derivative, if you recall the first method of testing, then we had that f dashed should be, I think it should be non-decreasing in nature, and your f double dashed, which is the second derivative, it should be non-negative. So yeah, one thing is to go analytically, but let me just show it to you in a simple way. Let's just try with maybe say x is equal to 0. Okay. Consider at x equal to 0, we have f dashed to be equal to a, right? At x equal to 1, we have f dashed to be equal to a to e to the power a. Okay, x equal to 2, we have f dash is equal to a to the power 2a. Now note one thing, say a is equal, let me write it separate. Say a is equal to minus 1. I'll just consider some simple examples. A equal to minus 1. Then the first value we have is minus 1 for only x equal to 0. We first have f dash is equal to minus 1. Then it becomes minus 1 into e to the power minus 1, which is simply minus 1 by e. Then it becomes minus 1 by e square, minus 1 by e cube, so on and so forth, right? Now turns out that e is something greater than 2, right? It's positive and beyond 1. E is greater than 1 and it's positive. So if that's the case, then what we have here is that, see, e is something positive. So e square, e cube is eventually increasing with time, right? So 1 by e square, 1 by e cube. Turns out that this would be decreasing with time, right? And so, sorry, decreasing with x. If 1 by e square, 1 by e cube are decreasing, then that means minus 1 by e, minus 1 by e square, minus 1 by e cube would now be increasing. This, since the sign is changing, the logic would also be flipping, right? So these are in, why can't I write it? These are increasing with x. Okay. What if I take, say, a is equal to now 2? Then f dashed at x equal to 2, then it becomes 2e square, then 2e to the power 4, 2e to the power 6, so on. Again, it's increasing with x. You can try with different values. Say you can consider, say, a equal to 0, then you always have 0. So constant, if you keep on trying, okay, and you would observe that it has a non-decreasing nature. It would either increase or stay constant. So our first condition is verified, right? Is satisfied, sorry, satisfied that f dash is non-decreasing in nature. Now we move on to the a square e to the power ax part. We have f double dash to be equal to a square e to the power ax, right? Now you notice one thing that, how do I say it? But you can pick out any value of x, okay? It's not syncing. Just a moment. Okay, so there is some network issue for which it's not syncing at the moment. But let me just keep on saying it until the internet is improved. So we have f double dash x equal to a square into e to the power ax, and a square is always greater than or equal to 0, and e to the power ax, if you try with any value of x and a, you check it, you will see that the whole expression that you have, this would also turn out to be greater than or equal to 0. Okay, so if a is positive, then of course a square to the power ax would be greater than 0. Otherwise, it can be greater than or equal to 0 only. So since it is non-negative in nature, f double dash x is non-negative in nature. Oh god, it's not syncing. So we can say that this would be a convex function. Just a minute, try something. Well, that's unfortunate. It's not appearing for some reason. But yeah, let me see if I can write it on another page. Anyways, we will just continue here. So turns out then the first conclusion was that this function would be convex, right? We will now move on to the next option. We were given f of x, I hope it comes, yeah, is equal to log x to the base e. And therefore f dash x would be 1 by x, f double dash x would be minus 1 by x square, right? And now you can see that for all x, your x square can be always greater than equal to 0 or less than infinity. Then turns out that 1 by x square can be less than 0 or equal to, sorry, oh god, infinity, right? Which turns out to say that, well, then that means minus 1 by x square is less than 0. So the equality sign, we will like ignore it for now, which simply means that it will be undefined. But what we mainly focus on that this is less than 0, right? So of course it's easy to cancel this condition because we wanted it to be non-negative, and it turns out to be f double dash x is negative. In fact, you can keep on trying for f dash x. You can see that as x increases, I'll just write the notation in this way, f dash of x, which is equal to 1 by x, is decreasing, right? But we wanted it to be non-decreasing in nature. So turns out in either case, this violates the requirements, and therefore it's a concave function. For the next example, we had f of x equal to mod x to the power a, where a is greater than equal to 1. So we can write this also as, you can check it on your own, like you can say that, well, this would be x to the power a if x is greater than equal to 0, or minus x to the power a if x is less than 0. So if you evaluate it on your own, you will see that this is given by this expression, and f double dashed is given by a minus 2, right? Now it's given to us that a is greater than or equal to 1. Okay, so that just means that, see, f double dashed x, yeah, so then this is greater than equal to 1, this is greater than equal to 0, right? This would also be greater than or equal to 0. So it is non-negative, right? Therefore non-negative. And if you focus on this a into mod x to the power a minus 1, then you have here this to be greater than equal to 1, and this to be greater than equal to 0, which turns out that this would also be greater than equal to 0. So if this is true, then just a minute, lost it. So if x is increasing, you will see that this function value is also increasing with time, and that means it is non-decreasing in nature. If it's non-decreasing, and that does the job, both the conditions are verified, and we have this to be convex. Now for the next option, we had, I think I'll just leave it to you guys with the hint that space E. So I'll just, yeah, this I can leave it as a hint, but I would like you to notice that this x that you have here, it can't be negative, right? So if it can't be negative or 0, because then that would lead to the undefined condition, then you can actually find out what would be the expression of f dash x and how f dash x would vary with x, and also what would be the expression of f double dash x, and then see why f double dash x, whether it's a constant or it varies with x or not, and if x changes, what happens to its value, right? So check on your own. Okay. This is a part left to you because it's quite straightforward, and you will end up getting whether it's a convex or concave. Let me see if that page appeared by now. Yeah, it came too late. Anyways, so we will now move on to the next part, which is starting from question number 4. And we have already read about affine functions in the basics, right? It means the function would be both convex and concave. So an affine function which is given to you, where a is in Rn, x is in Rn, and b is R, is convex and concave. So the basic thing you have to check is that whether this function is affine or not. But if there was no function, the statement would have been true anyways, that an affine function is actually both convex and concave. So let's just see whether the function satisfies the affine condition or not. That means it should be satisfying that equality part that we had, right? So let us consider 2 points x1 and x2. Okay. Now we have f of lambda x1 plus 1 minus lambda x2, where lambda is between 0 to, so it doesn't have to be between 0 to 1 actually for affinity, but if you are focusing on only convex and concave, then you can just look into the 0 to 1 range, right? In general, for any lambda, you see what happens. Turns out that f of lambda x1 plus 1 minus lambda x2, right? So the argument itself is lambda x1 plus 1 minus lambda x2. Therefore, we write f p A transpose lambda x1 plus 1 minus lambda x2 plus b. If we break it down, we have lambda A transpose x1 plus 1 minus lambda A transpose x2 plus b. And then note that we can break the b as lambda b plus 1 minus lambda b, right? So then if we bring it down together, we have A transpose x1 plus b plus 1 minus lambda A transpose x2 plus b. Okay. And therefore, this is what? This is equal to lambda into f of x1 plus 1 minus lambda into f of x2. And since the equality condition is satisfied, we can say that the function is affine, and that means it's both convex and concave. So I think, yeah, now the answer is very straightforward for you. Now, what about this condition? So we are given a quadratic function f of x, which is equal to x transpose qx plus c transpose x plus d. C is in Rn, d is in R, and x is in Rn as well. That means the vectors are arranged so that they are of conform dimensions. And it's given that q belongs to Rn cross n. Now we want this quadratic function to be strictly convex, right? So what was the condition of strict convexity? If we go back, there were several methods of testing, and out of which we saw that for strictly convexity property, we want the Hessian to be positive definite. So that's what we are going to evaluate now. So we have the function, well, instead of doing Hessian, you can also do simply double derivative, because here it's just given in a straightforward manner, right? So we have f dashed x would be twice x transpose q, the qx plus c, right? Because d is also a constant. So f double dash x is equal to 2q. Now given q is greater than 0. Sorry, I just gave away the answer, didn't I? So if q is greater than 0, then my f double dash x would be greater than 0 as well for any x, right? And if this is true, therefore for strict convexity, I just want my q to be greater than 0, right? What happens if q is greater than equal to 0? Then we get a simply convex function. If q is less than 0, we will end up with a, that means if q less than 0 means if q is negative definite, then we will end up with a concave, strictly concave function. If it's negative semi-definite, or that means q is less than equal to 0, we just get a simple concave function, okay? Now, one interesting thing to notice is that what if q is equal to 0, right? Because if q is equal to 0, that means it would be both convex and concave. In other words, it would be affine. Why? Because if this is 0, then we are simply left with C transpose x plus D, which turns out to be similar to this very form. That means it's a linear function or an affine function in x, right? So that was just a point which seemed interesting for this question. Now, what about this one? We are given two vectors x and y, and the angle between them is 60 degrees. So it's a very simple question. All you have to do is see what is x transpose y. It is simply norm of x to norm of y into cosine of theta, where theta is the angle between x and y. So it's very simple and it's very straightforward to do. The only thing you must be noticing is that is it possible for these two vectors to be having zero magnitude or to have their norms to be equal to zero? And if you think it a bit properly, you will notice that they can't be of zero magnitude because or zero, their norms can't be zero. If that's the case, then that means the vectors are simply like 2 points, right, on the origin basically. And if there are 2 points on the origin, then there is no meaning of saying that there is an angle between those two vectors, right? That means these two vectors are non-zero, having non-zero norms, and so you can then derive whatever would be the result. Let's now move to this question number 7. So we are given a convex function f of theta, which is given by theta norm of theta square minus a. Here theta belongs to Rn, a belongs to R, and theta is known to belong to a set called omega d. Okay, so f of theta is a convex function and theta belongs to omega d, where omega d is a convex set. It turns out you don't actually have to worry so much about this result. Why? Because it's given to you that omega d is defined by theta such that f of theta is less than or equal to delta. Okay. And f of theta is also given to you. So which of these following options would be true? Right. So see, simply put, how do I say it? The set omega d that is given to you. So this question is specific to the set omega d only. Why? Because since theta belongs to omega d, it will satisfy the definition of the elements in omega d, right? So see, this is only a set notation, just to make it clear. The question seems to be very straightforward, but one could have also written, like in exams, you can get this set in this form, say some z with f of z less than equal to delta. So if this was given to you, that omega d is a set with all elements of the form z where f of z, where z satisfies that f of z is less than equal to delta. Then think it in that way. So now it would become clear. So since it's given that theta, which is your actual parameter of concern, since that belongs to omega d, then that means theta will also satisfy, therefore theta will also satisfy the definition of the elements in omega d. What was the definition? That f of z should be less than equal to delta, right? This is the definition. This is how we are defining the elements in the set omega t. So therefore, this implies f of theta would be less than equal to delta. But what is my f of theta? F of theta is given by norm of theta square minus a, right? So we have here norm of theta square minus a is less than equal to delta. And then this is very easy to do. We do a side changing and then we take a square root. So this symbol will not flip. That is, will not become less than equal to y, because we are dealing with norm, right? We are dealing with the norm of theta. Let me just write the word norm. Since we are dealing with norm, had there been no norm, then we would have an upper and lower bound on both sides, with minus root over of a plus delta being less than equal to theta less than equal to root over of a plus delta. But since we are given the norm, we don't have to worry about it. It will only be the less than equal to sign. And I think, yeah, that gives away the answer to you, right? So not a problem. You have to find which of the following is true, not false. Okay. So let's just move on to the next part. Given the explanation of the basics, I think this would be quite easy to follow. We are given a function which is a function of x, y, and z. And is say that this is equal to minus x cube f of plus 4x square minus y square minus 3. So then what would be its gradient? Okay. So if we have to find the gradient, that means we are just doing the derivative, and we will be doing particularly partial derivatives here. So how do we define the expression? We had already written it earlier. Gradient of f is given by, I think we had it here, right? The basics. Yes, so you can see here we had two different variables. So grad f is simply dou f dou x and then dou f dou y. So we have this to be dou f dou x dou f dou y and then dou f dou z. Okay. Now what is the value of dou f dou x? We will differentiate with respect to x. Okay. So we have minus x cubed, that would become minus 3x squared plus 4 into x square will be 2x, right? And then minus 4y square, we will treat now y as a constant, so this will become 0. And then we have a minus 3, which should also become 0 because it's a constant. So I think we can close this bracket here. What about dou f dou y? Okay, it would be, see, minus x cubed. Here x is treated now like a constant, so this would be equal to 0. And then we have 4x square. Again, the same problem. 4x square would also be, when differentiated with respect to y, be equal to 0. And then we are left with only minus 4 into 2y, right? And same for minus 3, which is also a constant. Now, what about dou f dou z? See, there are no variables of z in this expression of f, right? So it turns out that if you differentiate it, all of these terms are treated as constants when partially differentiated with respect to z. And so we just land up with a big 0. So this is equal to minus 3x squared plus 8x, 8y, and 0. I think this is one of the options given here. Yeah. Now we move on to question number 9. Do we have time? Yeah, need to hurry up a bit. So this is based on projection operator, and if it's on projection, I think we can just go to the basics and discuss a bit on projection and then come back. So yeah, we'll now talk about the projection operation as a robustification of classical adaptive laws. So, Sir has talked about all of this, of course, dead zone, E mod, then sigma mod, projection. I'm not sure if we talked about the robustness owed to excitation or an exciting or persistently exciting signal. But we will focus only on the projection operation since the question involves that. So what is basically a projection operation? What is projection? It means something is outside a given region, so you put it back to that very region. You just project it back. Okay. You throw it back onto, when we say we are using a projector, it means we are throwing that light onto a screen, right? We are just letting it fall on a particular region. So suppose we are given a set. So this is a set. We do not know the exact value of a parameter, let's just call it theta, but well, it's not syncing again. Just a moment. Well, okay, so for some reason now this page is not syncing. So we'll just try it another page. anyways, it's not syncing, so let me just say it instead of writing. So if we do not know the exact, so given a set, if we do not know the exact value of the parameter, but we know that it belongs to a certain region, okay? It belongs to the certain region. And what we can do is, but we know that theta belongs to a set, say, let me call it a set S, okay? If this set is some S, then we use projection. Why? Because the common sense is that, say, when you are learning the unknown parameter by using some theta hat as an estimate, but is given to you that it lies within a range. Say theta belongs to from -2 to +5, right? So if your theta hat turns out to be +10, then there is basically no motivation or no point in carrying out your or designing your controller with that +10 value, because it's given to you already that theta should belong to -2 to 5. So what you do is you project it back and you say that, well, instead of -2, if it's 10, then I will put it back to the set, and the nearest value is 5 itself, which is at the border, right? So okay, there is no situation, yeah. So anyways, so that means then we will use the projection to put it back within the set -2 to 5. So if theta hat becomes to be 10, then you push it back and set it to be equal to 5. If theta hat comes out to be, well, it came, okay, good. If theta hat comes out to be something like, say, -3, then you again pull it back and put it to be equal to -2, right? So that's the simple idea. Now, what if it's a convex set? So this is my set S. This is syncing now. So this is theta, which is the true parameter, right? And you keep on learning. So say this is your theta hat, and whatever estimates you get. So you come at this point. So when you are at the border, what you do is, how does this projection thing work, right? So when you are at the border, you just check whether its derivative is pointing outside the set or towards the set, right? If it's pointing towards the set or inwards, then you do not worry and because see, if the rate of change is pointing inwards, right? If it's pointing inside, then that means the estimate trajectory would come inside the set only, and it won't be leaving the set, right? Which makes sense to you, that's what we want. But if it's pointing outside the set, then what we do is, instead we take the then what we do is we just take the tangent. We find what is the tangent and we increment the change in theta hat along the direction of the tangent. So that's where the idea of this directional derivative appears, right? So if we just write it down for you, what happens if it's along the tangent, then simply it won't be leaving the set, it would rather be on the boundary of the set, but that means it's still inside the set, right? That's what we want. So it would basically be on the boundary, and maybe in your next turn, if you have better luck, then it might get inside the set, right? If it gets inside, it's fine. If it doesn't get inside, and if it again goes back to, say, it has and it makes an attempt to come out, then you again push it back towards the set so that it again gets inside the set and keeps estimating. And you can only hope that it goes as close as possible to theta star, which is the true parameter theta, right? So if I have to write it down just for a quick grasp, so we start, do we have time? Yeah, we start learning with theta hat not that belongs to the set S. Okay, so it's quite understandable why would you take the set S, because there is no meaning in choosing your theta hat not to lie outside the set, right? Since it's a given knowledge to you that the true parameter also belongs to theta. So then we use the classical method let me say classical adaptive methods. Adaptive methods to learn theta, right? If theta hat at any time t goes greater than anytime t greater than 0, if it goes outside, if it's directing of course inside this set, then there's nothing to worry, right? Reaches the boundary, it reaches the boundary, then check the following, check the following. Number one, if the derivative is pointing inwards, that means towards the set, then there is no need to change, then no modification is needed, and we are good to go. Okay, if the derivative is pointing outwards, then we will do the projection modification, then do the projection. So I will just write, then modify the update law by considering its tangential component So if you recall here, this light green line was this tangential component, right? So maybe I'll just make life easier for you, changing the color. This is this, fine. Okay, so I think the color coding would help you understand which direction we're talking about. So we consider its tangential component so that theta hat will again belong to the set S. And why is this crucial? So why is this crucial is because we are now focusing on models of the form X. Sorry, we are dealing with this, not with continuous time. X dot is equal to AX plus BU. If we have some disturbance or some structured uncertainty, some unstructured uncertainty, some mismatch, whatever, if we have this term, there is a chance of parameter drift, right? The estimate might go unbounded due to the presence of the disturbance. So the motivation of doing projection is that if we can ensure that theta hat would belong in S, then and parameter drift would then be avoided. So that is the basic motivation for doing the projection operation. So if we focus on the questions, I think we can look into this a bit later, but let's just see question number 10 first. What does 10 tell us? It has which of the following are not true about the projection based modification. So let us just see the options. Okay. So if we have the knowledge of the upper bound of the disturbance is necessary. This is what they say. But notice here, when we design this projection operation, we never talked about what is the upper bound of the disturbance. We just wanted that the disturbance should be bounded. Okay, it can't be infinite disturbance, makes no sense, right? So it whether the knowledge of the upper bound is necessary or not. So well, it's not necessary, right? That's what we just saw when we designed the law. Then we have convex function f is required such that f of theta should be less than equal to delta, where delta is greater than 0 and theta is the unknown parameter vector. So if theta is the unknown parameter vector, you need some convex function f such that f of theta should be less than equal to delta. And what's the difference with the third option? It just says that well, f of theta should be less than delta. Now, what do we get by the difference between this less than equal to and simply less than? Notice one thing. When we are doing or checking for this convex set, right? I can just write it down. It belongs to a convex set. Convex set. So when we are doing this derivative, or when we are finding the tangential by doing the derivative at this point, we are checking the condition at the boundary, right? So if we do not have a boundary, then how do we do a derivative at that point? That is not possible, right? Because f of x would not be defined at the boundary. So I hope it's, I don't know if it's clear or not, just to emphasize on it. Given that a function f of theta is less than equal to delta, say theta is equal to theta 1 square plus theta 2 square, which is less than equal to 2, right? If it is said that this is less than equal to 2, only then can you draw a circle with radius equal to 2, sorry, root 2. Okay. This is possible to be drawn only if the less than equal to is given. Otherwise, what you will have is, if I say that theta 1 square plus theta 2 square is less than 2, then what you will have is only now a region will have a region like this. So pardon my drawing is not very accurate. And where this theta, this dashed line represents a simple boundary. But this yellow figure that you have, that is not touching the boundary. And if it's not touching the boundary, that means there is no theta lying at the boundary, right? And if there is no theta lying in the boundary, you cannot find this derivative at the boundary. So it makes no sense of how you will apply the simple projection operation that we studied in the class. So the condition that for projection, you actually need this less than equal to sign instead of only the less than sign. Okay. So mind it, when you select for the answers, you have to give which of these are not true. Okay. And then this is the last question for today. And it is relevant to this very part that we discussed. Where is it? So we will check at the boundary. What we do is we will check if the derivative is pointing inwards, then no modification is needed, right? If the derivative is pointing outwards, then we will use the tangential component. So let's see how we can actually do it. So maybe I'll just write it down as okay. So what does the question say? In projection-based modification, the parameter updation law of theta, which is unknown, is given by theta hat dot to be equal to y when f of theta hat is less than 0 or y transpose grad of f of theta hat is less than equal to 0, right? Note that y is the derivative of theta hat. So basically, y is equal to theta hat dot. This is given to you, okay? Y is equal to theta hat dot because y is the derivative of theta hat, right? F is a convex function, which is very good for us. If it's a convex function, then f of something, f of theta less than equal to something would lead us to a convex set, right? And alpha is some matrix in R n cross n. Now, consider this very function, which is theta 1 square plus theta 2 square minus a. Then which of the following relations are true for alpha? Notice one thing, we are given here two cases. One with y and the other is y minus alpha y, right? So see, y is equal to theta hat dot, right? Y is equal to theta hat dot, which implies for the first case, let me highlight it with yellow. For the yellow highlighted case, there is no modification, right? Right. So basically this is the case which corresponds to the derivative is pointing inwards. So this condition that you have y transpose grad f theta hat being less than equal to 0 means the derivative is pointing inwards the set. So that's why we didn't have to do any modification. Which therefore no modification was done. Now what is the other option that we were given, other case? We were said this is equal to y minus alpha y, otherwise or when y transpose grad f theta hat is greater than 0. So this is the case when the is actually pointing outside. Okay, so in usual scenario, what we do is for the otherwise case, I'll just write it down. For the otherwise case, theta hat dot being equal to y minus alpha y, what we say that is that we were actually going to use the tangential direction, right? We were actually going to use the, I'm just writing it in this way. Okay, let it be like y and theta hat. So this is what we wanted to do, use the tangential component. And how do we define it? We say that, well, the tangential component is basically, this is the projection of y along the tangential component of the derivative. Okay, I'll just write it. So which is along the tangential component. So y was the derivative, right? You could have been you could have selected the normal direction or the tangential direction along that set at that very point of concern. Okay, so which is one of the boundary points for sure. So this is simply equal to how do we write it? We say this is equal to y minus, sorry, y transpose grad f divided by no grad f square norm square into grad f. Okay. So this was done in class, so I will not be going into the details of how we derive this. And then what we have is y minus, we can also write it as grad f transpose, right, into y divided by grad f squared. Sorry, grad f norm squared. So what was f? F is theta 1 square plus theta 2 square minus a. So we have f is equal to theta 1 square plus theta 2 square minus a. Therefore, grad f would be dou f dou theta 1 dou f dou theta 2, right? Because we have now two variables, theta 1 and theta 2. So this would be twice theta 1, twice theta 2, and a is a constant. So turns out that this becomes equal to let's not put it in this way, because see, it was given to us that this is equal to y minus alpha y given, right? So therefore alpha is equal to grad f into grad f transpose divided by norm of grad f square, which is simply equal to, if we replace this, we have twice theta 1 twice theta 2 into twice theta 1 twice theta 2 divided by norm of grad f square. And then this becomes equal to 4 theta 1 square 4 theta 1 theta 2 4 theta 1 theta 2 and 4 theta 2 square divided by norm of grad f square. Okay, so let's just see if this option is available. Yeah, the option is given in one of this, right? So which of the following relations would be true? I think that is clear. So yes, I think we have discussed all the questions in the last assignment. If there are any doubts, you can of course ask it in the discussion forum page, which is given under the Q&A section. Or if you have questions now, you can ask now. I will be waiting for 10 more minutes and then we will end the session here. Okay, so I think we can end the session here. There are no more doubts, of course. So yeah, sorry. So we will be ending the session here since we have no more doubts, and can stop presenting. So thank you all for doing this course. I hope you all uh, got to understand very well about nonlinear and adaptive control, at least get a basic grasp of this, and hope you all the best for the exam to whom all those people, all those enrolled students who are going to attend the, are going to write the exam. So that's it, and we will be ending the session here. Thank you for listening. Bye.